Well, now we want to relate this important aspect of energy to power, and we've just done that with the Saturn V rocket. We took the amount of energy contained in the fuel, we divided it by the burn time, and out came the power output. Now we want to turn our attention to the sun. We want to calculate the power output of the sun. This sets the high end of all power aspects that we're going to be dealing with, and so we might as well start at the top, and let's see how we calculate the energy output of the sun. And just to remind ourselves, when we switch to power, the unit is watts. And again, 1 watt is equal to 1 joule per second. So we always remember that power is energy per unit time. Well, when we think about the sun, it's a very complicated body, actually, because it's driven by the nuclear reaction converting hydrogen to helium. And we're going to study this in detail in the chapter on nuclear energy. But there's some remarkable features. One of them is that the center of the sun, the core of the sun, which converts that hydrogen to helium, that operates at a temperature of 100 million Kelvin. 100 million Kelvin. That's 10 to the 8 Kelvin. That's, needless to say, an extremely high temperature. Then what happens is that very hot core transmits that energy through a combination of radiation, electromagnetic radiation, thermal motion, the very large overturning structure that's intrinsic to the sun, and finally it delivers that to the outer photosphere. The photosphere is what we actually see when we look at the sun. And the photosphere is the outer defining membrane of the sun itself. And that photosphere emits at 5,800 Kelvin. So the temperature is dropped from 10 million Kelvin to 5,800 Kelvin. The next thing is that to calculate the energy output of the sun would appear to be an extremely complicated process. All of these issues are going on, and how could we possibly actually determine the power output of the sun? Well, it turns out it's a remarkably simple calculation, and it's based on the Stefan-Boltzmann law. The Stefan-Boltzmann law tells us that the power output of any body that's emitting into the domain around it can be calculated by multiplying the area times the Stefan-Boltzmann constant times the fourth power of the temperature. That's an amazingly simple expression. If I can calculate the area of the sun and I have the surface temperature of the sun, I can calculate the power output. But the other thing to notice is that the fourth power dependence of the temperature, this is exactly why when you pour hot coffee into a mug, it actually cools very quickly, because it's emitting with exactly the same process that the sun emits, and that is the oscillation of positive and negative charges intrinsic to the surface generates the identical relationship between power and temperature. So a cup of coffee is going to cool very quickly in the beginning because the temperature is higher, so the temperature of the fourth raises the power output. So let's come back to the sun and see how simple this calculation is. The first thing I have to do is calculate the area of the sun. And the area of the sun is simply equal to 4 pi times its radius of the sun squared. And the radius of the sun is 6.96 times 10 to the 8 meters. So that means I have 4 pi times that radius, 6.96 times 10 to the 8 meters. And I square that, and that means that the area of the sun gives me 6.09 times 10 to the 18 square meters. Now the next thing is the Stefan-Boltzmann constant. And this is one of the most fortuitous examples of one of the most important constants in nature, because as we'll see, nature interchanges energy amongst these categories we've talked about in large measure by exchanging infrared radiation one to the other. And so the Stefan-Boltzmann constant is always coming into play when we're calculating the way in which nature exchanges energy amongst these categories. But look at what the Boltzmann constant is equal to. It's equal to 5.67 times 10 to the minus 8 watts per square meter Kelvin to the fourth. So 5, 6, 7, 8. You can remember this very easily that way. And then, of course, the Kelvin to the fourth is what cancels out the T to the fourth, but we already know what that is. That's 5,800 Kelvin. That's the temperature of the photosphere, which is what we see. And so I'm going to be taking that to the fourth power. Well, all I have to do now is to plug those numbers in, and I have calculated the power output of the most powerful entity that we will study. And so the power of the sun, when I plug in all of those numbers, is equal to 3.9 times 10 to the 26 watts. That's equal to 3.9 times 10 to the 26 joules per second. That is the number against which all else is compared.